Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open the session and I welcome you to the public defense of Jacob Harold Pember. Jacob Harold Pember has presented to the faculty the PhD thesis on the topic, the Marvel Exoplanet Array technologies for high precision radial velocity exoplanet detection, in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. Mr. Pember shall now publicly defend the PhD thesis. You are invited to give a presentation of about 40 to 45 minutes maximum about your work. And after that, we'll follow a discussion with the members of the examination committee. You have the word.
Okay. Hi, folks. You're all very welcome, especially those of you who have traveled to be here today. Yes, today I'm going to be talking about some of my work from the last 4 years on this project, the Marvel Exoplanet Array. So what is this? Well, I'll get into it a bit more later, but this is a new facility of 4 telescopes, 4 80-centimeter telescopes. So these are not huge telescopes. These are, if you're a very rich amateur, you could have one of these in your backyard, maybe 2. So this is sort of on its way to being installed next to the existing Mercator telescope on La Palma that the Institute runs. So today I want to talk a little bit introduction to exoplanets and how we study them, the relevant detection methods and sensitivities and sources of noise. I'll talk about the Marvel facility itself, of course, an overview to this, some of the requirements of this facility to make the detections that we want to be able to make with it, and how these requirements then feed down into what the instrument looks like. In terms of the instrument architecture, this comes directly out of these requirements. All of the design choices that were made along the way during my last 4 years flow down from this. I'll talk about the wavelength calibration system. This is one of the most important parts of this, of a system like this, an instrument like this. And then at the end, I'll go over some of the future challenges, because this is not yet operational. There's quite a lot of work yet ahead for this. So exoplanets, what are they? These are planet-sized objects. Now, this could be from very, very small to something several times the size of Jupiter, orbiting stars other than the Sun. So the first such objects were detected in the sort of early and mid 1990s. Sorry. And until now, there's something like 6,000 exoplanets that have been found around other stars. There are a lot of different types of exoplanets, and especially different types of exoplanetary systems. This is one of the most surprising things to come out of this branch of science, that you see all kinds of things that are very different to our solar system. So here you see the solar system, these concentric circles, maybe a bit hard to see, but most of the systems here are much more compact than the solar system, with planets much closer to the star than even the Earth is, let alone the outer planets. So there are a number of ways in which such exoplanets can be detected. You might think that imaging these directly is the most obvious and logical thing to do, but this is very much not the case. Stars are so much brighter than any light we receive from the planets, and so we go with indirect detection methods. I'll talk today a bit about the radial velocity technique and a little bit about transits. Now I'll explain those in a sec, but just be aware that there are several techniques of finding planets. There's a lot of information encoded in light. So starlight comes to us, looks white or more or less continuous until you disperse it into a spectrum. So you see here a sort of compiled spectrum of the sun, and you see all these features. You see lots and lots of absorption features, black lines in this spectrum. These correspond to energy levels in atoms and molecules that are present in the sun's atmosphere. And so this information that's encoded in a spectrum, this gives us a handle on detecting what is this object, the star, doing at that point. In particular, it's the location of these lines and the movement of these lines over time that we want to detect with MARVEL. So the radial velocity technique, also abbreviated to RV, also Doppler spectroscopy, these are all the same thing. It is measuring the Doppler shift, the red shift and blue shift of these spectral lines, this spectral information over time. So in this little animation here, you see a star in the center, a planet orbiting around, and the star, in fact, orbiting around the common barycenter, the center of mass of this system. And so that star is moving with a reflex velocity, dragged around by the planet as it orbits. As it does so, the spectral lines shift, red and blue, as it's moving towards you. So in this figure here, the planet is moving away, but the star is moving towards. And so the star light itself is blue shifted ever so slightly. In the middle panel, there's no radial motion, no motion in the direction of the line of sight. And so there is no blue or red shift impacted here. And then in the right panel, the star is moving away, and so its light is red shifted. When we talk about the level of precision that we want to measure, how well do we want to know the velocity of that star at a given time? There's sort of a rule of thumb that we talk about precision radial velocity down to a few meters per second. So that's a sort of quick jog pace that you measure the velocity of this full star, the center of mass of this star, or extreme precision down below 1 meter per second. So that's walking pace to measure this velocity. The other technique I mentioned, transits. So this is a photometric method. We measure the brightness of a star over time. And if the system is lined up just right, and the planet passes in front of the star from our line of sight, you get this sort of mini eclipse, the transit. And so measuring this really gives you a handle on that, yes, there is a planet there, or there's a planet, something that looks like a planet in the signal. This gives you a lot of information about what this planet is, what type of planet it is, how large it is, the radius of the planet. combining transit detections with radial velocity measurements gives you even more information. It then gives you the mass of that planet. And so you can measure, you combine mass and radius, you get the bulk density of this thing. So you can start to distinguish between, is this a super Earth planet? Is this a sub-Neptune planet, something a bit more gaseous? And you start to do much more interesting science than either of these methods by themselves. So I already mentioned Marvel. This thing is going to be a dedicated facility for radial velocity measurements. It's going to be robotic, so no human in the loop as far as making observations. We'll be able to run all night, every night, as long as it's clear, taking these measurements. It's designed for really automated survey work to cover a catalog of target objects and use up the time as efficiently as possible. As I said, it's 4 80-centimeter telescopes in these domes behind me here, and these feed by optical fibers a single large high-resolution spectrograph in the room beneath me in that picture. So this is a concept diagram of what that looks like. All of these lines are optical fibers linking from the telescopes into the one spectrograph. Okay, so the tricky part here is, what is the scale of the thing we're trying to detect? So 1 meter per second, I said this before. This is the precision with which we want to know the radial motion of this star, whichever star we're looking at. Why is that hard, or indeed is that hard? Yes, it is. So here you see a series of images, starting with me on the left holding a broken, I hope, detector. So this is the same size as the detector that we'll put in the Marvel spectrograph. So then in the next picture, you see this little red box. This is just the corner of that detector. Here's the corner. We zoom further in to see the pixels themselves. And then on the far right here, these are silicon atoms in a single pixel. So the measurement that we want to make is on the order of 13 nanometers. This is extremely difficult. This is something you can't just do by looking at one spectral line. You need to look at many thousands of these and use all of the information that you have at your disposal. So we have this goal of 1 meter per second measurement precision. This feeds down into several key things that dictate the way this instrument has to look. The first is that it needs to have high spectral resolution, and I'll cover these in more detail in a second. The second is broad wavelength coverage, so we collect as much spectrum as possible, as many spectral lines, as much information as possible. It needs to be extremely stable, as in nothing is changing at that level of 13 nanometers over time. It needs to have extremely reliable calibration, which I'll talk about as well. And something a bit more particular to the Marvel case is high throughput, efficiency of the system in terms of photons that come into the telescope. How many of these do we actually end up detecting? So if you see this little bullseye target symbol, I've put this throughout the slides to pinpoint things that drive the instrument design. Okay, so the first one is high spectral resolution. Spectral resolution is a measure of how close two features can be in terms of wavelength and still be distinguished from one another. So the higher the spectral resolution, the closer two features can be and be distinguished. So the typical level at which we talk about is that the lines in the star are fully resolved. That means that going to higher resolution doesn't sort of give you more information about the line itself in terms of position. This happens at around a resolution of 40,000. Now this number is a bit, without going into further detail, it's just a measure of the resolution. Higher is more power to resolve features from one another. Typically, we go even higher than this baseline limit. So we care not just about the positions of lines, but also about the shapes of spectral lines. So you can see in this diagram here, at a resolution 10,000, the blue line there, you really don't understand anything about this spectral line at the top. At 20,000, you start to see that, yes, it has some structure, but it's maybe only over a couple of pixels there. At 45,000, you start to be able to tell where the center is of that line. At 90,000 and above, you really start to measure the shape of the spectral line rather than just its position. So we also need broad wavelength coverage. Now, I showed that spectrum earlier. Here you see a small slice of it. The broader coverage you have, the more of these spectral lines will appear in your data, the more information you capture. So we want as broad as is practical. You can, the spectrum continues forever in both directions, but it starts to get into very, very different instruments too far beyond the visible range. And so we wanted to push as wide as possible, but without further specializing the instrument into extreme cases. So a typical precision radial velocity instrument will cover from 450 nanometers, this is sort of towards the UV end of the spectrum, to at least 630 nanometers in the sort of reddish orange parts, or further, broader than this. We also care about specific wavelengths a lot more than we care about others. So one reason that we care about this is to understand activity of stars. So a star is not just a perfectly spherical emitting body. There is activity on the surface, and this can really play havoc with this kind of detection. Here you see in the figure on the bottom right, a Doppler map of the sun. You see one half of it is coded blue here. This is the half that's coming towards us as the sun rotates, and the red half is going away. Above that, you see a sort of basic simulation of a star spot. Lots of stars exhibit spots, features on the surface, either dark or bright, that change over time. And these mask out a certain part of what you see below. And this can look exactly like the signal of a planet. If you mask out part of the sun that's coming towards you, then on a whole, the sun looks like it's then moving away from you because you've blocked out part of that light. So there are a few key indicator lines of activity like star spots. And so we wanted to cover as many of these as possible for the Marvel instrument. So here I've listed the sort of extreme ends that we went for. Calcium, H and K lines. This is in the near UV, and also calcium, but then in the near infrared, a triplet of lines. So we aim to span this entire range from 390 to 870, or indeed beyond. Stability of an instrument like this is extremely important. So this is because measurements like this, if you want to measure a planet orbiting around a star over time, these measurements, you get a single data point from a single measurement, and you need many such data points, 50 or 100, over the span of a year or more to fully characterize a planet's orbit. And so the system needs to be stable over this kind of time frame, even down to the level of a few tens of nanometers, like I showed before. So this feeds down into the system design, that the instrument should be in vacuum and well controlled in pressure, in temperature, mechanically well controlled, stabilized. To put it in vacuum, this also feeds down to using optical fibers to link from the telescope to the instrument, and to put it in its own dedicated building. I've used a few words that I think it's important to define a bit better. So this is accuracy, precision, and stability. So here you see two sort of simulated traces of data, whatever, over time. The accuracy of these points describes how far the measurements are from the sort of ground truth, if there is one. So here the x-axis itself is ground truth. So you can see the blue trace on the top is more accurate. It's closer to this value. Precision is the spread of values from its own, their sort of own self-consistent average value. So you can see that the blue trace on top is less precise. It's more spread out, and the orange trace below is more precise, even though it's less accurate. And stability here, this is the shift in accuracy over time. Now, you can also have a shift in precision over time, but I won't discuss that. So you can see here that the top trace, the blue trace, is more stable, even though less precise. It's more or less sticking about the same value, whereas the lower trace has low stability, even though it's more precise. So these things we care about very much in the type of measurement that we're doing with Marvel. We care not so much about accuracy. It's very difficult to make an accurate measurement. You don't always have a ground truth anywhere to compare to. We care about precision, and we care about stability. We care about these in the context of wavelength calibration. So in order to measure the position of lines in a spectrum, we need to measure these against something, some known and controlled spectrum that is very well characterized. And so this would be a calibration spectrum, from a wavelength calibration source. So this is a critical part of any radial velocity measurement at this precision. And so it's worth discussing further. So I'll take a short detour about wavelength calibrators over time and sort of what is the current state of the art. So historically, one of the first ways that was used to calibrate a spectrum is to look at the lines, spectral information that's imprinted from the Earth's atmosphere in really the last few kilometers of the travel of this photon through the universe. And so you see here an example spectrum with this region up the top circled. These are all lines from the Earth's atmosphere. They're called telluric lines. They're generally thought of as being a contaminant to spectra these days, but historically these were used as a reference standard against which another spectrum could be measured. However, the limiting precision of these lines gives you only 100 meters per second at the very best. So this doesn't quite cut it for what we're talking about. So the next kind of step in increasing precision with wavelength calibration was gas absorption cells. So here, this interesting looking contraption is a gas cell with molecular iodine inside. Now this is put behind the telescope and in front of a spectrograph, and it sort of imprints its own spectrum, just like the telluric lines from the atmosphere, but here now in a much more controlled way. So this here can be kept thermally stable over time, so it's a bit more trustworthy. Unfortunately, this also sort of contaminates your spectrum. It masks away parts of the spectrum by imprinting this new signal. And it has a limiting precision of something like 10 to 15 meters per second. So it's also not at the level that we care about. So instead of using absorption in a spectrum to use as your wavelength calibrator, you can also use emission spectra. So this is still commonly used in many instruments, to use a hollow cathode lamp that has particular atoms inside, excite these, and these will glow at very particular wavelengths. You see here spectrum from a thorium-argon lamp. So you see lines from both thorium and argon in this spectrum. This gives you a lot of reference lines that you can look at and measure your spectrum against. However, they vary in both brightness relative to one another. They vary in spacing between one another. In fact, a lot of these blend together, and so it makes it very difficult to use. And these lamps also can change over time. The limiting precision of these, however, does get you into the range that we're talking about, a few meters per second, perhaps. So what is the ideal wavelength calibrator? Well, it has spectral lines that are equal brightness, so they are all the same brightness across the spectrum that you use. They are evenly spaced, but they're also densely spaced. So it's no good having one line every so often. You want them to be quite close together. They should cover the entire bandpass that the instrument sees. So this is really, as I spoke about before, from 390 to 870 nanometers or so. You want these lines to be spectrally very narrow, as in narrower than the instrument itself can resolve is ideal. You want them to be very stable, both in brightness, as I've talked about, but also in wavelength, not shifting in their positions over time. So to add to this list of this sort of wish list, the system should also be reliable and not having to require any interventions over time. Maybe cheap as well. Maybe that's asking too much. So there are two kind of current avenues to wavelength calibrators that exist. So you have on the left laser frequency combs. This is quite a large, complex but self-contained system. And on the right, an illustration of a system based on a Fabry-Perot etalon. So I'll talk about these. Laser frequency combs, they indeed produce this ideal or near ideal spectrum that gives you a whole bunch of equal brightness, equally spaced, densely spaced lines who you know their wavelength. These are a commercially available system. However, they are very expensive. I've put down the bottom, €6. That's maybe the exponent in the price. The other system built on Fabry-Perot Etalon. So this is a passive optical system where you have light, white light that you feed in that is bounced back and forth between two mirrors that form a cavity. And only light that fits perfectly in this cavity in terms of its wavelength gets transmitted through. As I said, that's a passive system that was quite a bit less complex than the laser frequency comb. And it's quite a bit cheaper. I've put €3 there. But in such a system, the true wavelength of any of the lines is not known by default. So you need to calibrate the calibrator by measuring the wavelength of one or more of these lines against yet another external reference. So this makes it a bit more expensive and a bit more complex. So the wavelength calibration system is actually more than just measuring the positions of spectral lines over time. If it is stable in itself, the system can track the drifts within the instrument. So this, getting down to somewhere like 1 meter per second, this is really a critical step. And so it highlights even further the importance of calibration. To do this in the best possible way requires measuring the calibration spectrum next to every stellar spectrum that you take. So here you see a little inset of a simulation from what the spectrum in Marvel will look like. See, on the left of each of these bundles of lines is the calibration spectrum. So we have a fifth input to the spectrograph as a feed down from this importance. With Marvel, we also care very much about maximizing the throughput of the system. So the fraction of photons that enter the telescope that do end up being detected at the detector, typical for RV instruments, is 10%, maybe less. So that means 90% of all photons are lost in the system. So we really tried to, in all of the design steps, maximize this wherever possible. Because we have small telescopes, it makes it even more critical than in a system at a larger telescope, where if we can gain 1% or 0.5% anywhere, that really, we feel that benefit immediately. So all of these requirements that I've discussed, they push towards a single instrument architecture. And because they do, it's perhaps unsurprising that radial velocity, the field of radial velocities has kind of standardized around this architecture. And that is a white pupil relay cross-dispersed Echelle spectrograph. Now, I'm aware that this is kind of very jargon-laden, and so I'll explain the three parts of this phrase here. So first, Echelle. What is Echelle? This is the type of diffraction grating that we use in the instrument. Here you see me posing next to the Marvel grating. You see on the right me posing in the reflection from this grating. Now the weird thing is this reflects my face back at me under an angle of 70 degrees. It's really super strange to see in person, but this is how this type of grating works. You see in this inset down the bottom, these steps, these grooves in the grating. These form the diffraction grooves, and reflect light, depending on wavelength, at quite a steep angle. So cross-dispersed, I'll go back for a second. When this grating disperses light, it disperses it into a large number of what we call diffraction orders. So these are different parts of the spectrum, different chunks of that wavelength range that are distinct from one another. And after the grating, these are all kind of overlapping. And so it needs to be separated somehow. You can either filter out 90% of all your light to leave just one of these, or you can disperse these yet again in the orthogonal direction to give you a big 2D spectral format. And so that's what we do here with a cross disperser. In our case, it's a prism, a very large, it's more than 40 kilograms block of glass. And this forms our cross disperser, the instrument. And what is a white pupil relay? Well, this is an optical layout that kind of images the state of the beam of light from the location of the grating here in yellow onto the other side, the location of the cross disperser, the prism. This has two effects. It folds the entire instrument into a sort of much more compact footprint, although you have quite a complex back and forth bouncing of light in this part. It also keeps the size of the required size of all these optics as small as possible. And this is a very common layout for these types of instruments. So the vast majority of radial velocity instruments, I've listed a few there, use such a layout. So Marvel ends up looking like this here. There's a cartoon of it. It uses the white pupil relay. It's built around a single collimator mirror. That's this guy down here. Uses a single arm. So we have a single set of optics throughout from start to finish. We use one large detector on this. We in fact have two resolution modes, one at 90,000 and one even higher at 135,000. And to calibrate this system, there will be an Etalon, a Fabry-Perot Etalon wavelength calibration system. This is what the spectrum at the detector of Marvel will look like. So you have left to right in this image, the dispersion direction. This is from the Echelle grating. And then vertically, you have the cross dispersion, the effect of the prism to separate all of these orders. You see each order, each bundle of the 5 spectra. So you have 4 from the telescopes on top. These are the spectrum of a star. Below this, you have the calibration spectrum alongside simultaneously. This is the coverage of the spectrograph in terms of some of your favorite spectral lines, I'm sure. So you see the family of common stellar spectral lines here. Circled, I've put the calcium H and K and the triplet lines that I talked about before, the activity indicators. So we cover these and beyond. So today, this very day, Marvel is still being put together. So at the mountain, we have the 4 domes that you see in the picture. These, all 4 of them now have telescopes inside, but yet the spectrograph building is still sitting empty. It's still several months away from being completed. And some of the most challenging work is still ahead of us, in fact. Achieving the precision that we're aiming for is not a given, and so it's something that has to be fought for every step of the way. including after it's installed at the mountain. So in the last few minutes, I'll talk a bit about the future challenges for Marvel and how these might be tackled. So the first is stability of illumination of the system. So we feed with optical fibers, and many people assume that an optical fiber, you shine light in one end, the same exact light shines out the other end. Simple. But it's not quite so simple. That these do have all kinds of behaviors that can complicate the measurement that we're trying to use. So in this image here, you see sort of speckle pattern when you illuminate a fiber with monochromatic laser light. In our spectrograph, the dispersion is high enough that every pixel sees more or less monochromatic light, and so we are affected by speckles like this. You see in the red image here several of the modes that are allowed to propagate in optical fiber, and the speckles that you see are a combination of these modes. Very complex and very difficult to predict at times. So in order to smooth this out over time and get stable illumination of the instrument, there are several techniques. I've listed a few here. Fast dithering of the star image onto the fiber during an exposure to illuminate different parts of this fiber differently. Mechanical agitation, this is literally shaking the fibers, or a double scrambler, imaging one fiber onto another fiber. So this is the largest of the optical concerns of the instrument. Also, the environmental stability of the thing needs to be stable at that level of 13 nanometers over long time spans. So this is tricky to achieve. We have measurements here from the Hermes spectrograph at the Mercator telescope. The sort of range in deviation in temperature there is at the level of 10 millikelvin. We want to go an extra factor 10 better than this. So that's going to be another of the challenges. I talked a lot about wavelength calibration. And indeed, this is having a good quality wavelength calibrator is not such a straightforward thing either. So there's quite a lot of work that needs to be invested in this. The Fabry-Perot wavelength calibrator that I discussed is not necessarily stable over time. The wavelengths of each individual peak may shift in strange ways that are very difficult to measure unless you have something like a second calibration system to measure them against. So as part of my work in the last year and a half or so, I measured such a system that we delivered to KPF, the Keck Planet Finder. It's a similar instrument at the Keck telescope in Hawaii. Here you see the drift of this Etalon system, which is similar to the one we want to install at Marvel. This one is drifting at 3 centimeters per second per day in bulk, but then you get some drifts around this that are different at different wavelengths. This is going to be a big challenge. And lastly, and perhaps the most difficult of these challenges to face, is stellar activity. So since the last several years, there's been little in the way of improvement in precision that RV instruments have been able to achieve. Up until maybe 2010, every year was getting better and better results, and then hit a sort of noise floor, which is coming from the stars themselves. So the stars oscillating, noise on the surface, any activity, star spots, bright spots or dark spots, this becomes difficult. This is sort of outside of the Marvel instrument, let's say, but becomes a very significant challenge to reaching that final precision. And with that, I'll leave today's presentation and welcome any questions.
Okay, thank you, Jake, for the nice presentation. Let me now introduce to you the members of the examination committee, and I will start with the supervisors of the work. So they are Professor Christian Schwab from the Macquarie University of Sydney, Australia, and Professor Hans van Winkel and Dr. Geert Raskin from the Department of Physics and Astronomy, Astrophysics Unit of the KU Leuven. Other colleagues in the examination committee present here with us today are Professor David Coates from Macquarie University of Sydney, Australia, who is with us online. And then here, Professor Denis Defrère, and also from the Astrophysics, Astronomy Unit of KU Leuven, Professor Chris Glorieux, my colleague from the Soft Matter and Biophysics Unit of the same department. And also during the previous examination meeting that we had, so we had previously a preliminary defense when the examination committee members had a thorough discussion with Jake. And other colleagues have joined us during that session, and they were Dr. Michael Weber from the Leibniz Institute of Astrophysics in Poznan, Germany, and Professor Francesco Pepe from University of Geneva in Switzerland. And myself, I'm Carmen Bartik from the Soft Matter and Biophysics Unit of the KU Leuven. And with that, I would like to invite Professor Coates from Macquarie University. Maybe he has some questions or remarks or comments for Jake. Would you like to start the discussion, maybe?
Thank you very much. And thank you, Jake, for a very nice presentation. Jake, I'd like to take you back to the headline goal for the instrument, which is the 1 meter per second precision target.
David, I'm sorry, David, we have some looping audio here. You're getting remixed on the fly.
Do you want me to just slow down, or is it not working at all? Maybe we try that. Is that working better? Did that work, Jake?
Yeah, we can hear you, David.
Shall I try again now then?
So you hear us now, David?
I can hear you, and that audio does sound a bit different. There's no buzzing for me. Am I coming through more clearly?
I don't like this at all. The problem is we get Can you try again, David?
Certainly. Am I coming through clearly now? Maybe it works better when the room is muted. And is that thumbs up is for me, I believe. Is that right? You can hear me. Assuming you can hear me, if someone in the front row could indicate with a thumbs up that you can hear me, fantastic. Thank you very much. So thanks, Jake, for a very nice presentation. I wanted to just start with the top level science requirement, which was the 1 meter per second precision. And we just saw data that showed instruments are looking and doing detections, many of them at much lower precision. So why not aim for a slightly easier target, say 3 meters per second, or in the other extreme, why not aim for 30 centimeters per second precision? Why have you settled on 1 meter per second precision? And I can't hear you now, of course.
Okay. Hi, David.
I missed your answer.
Sound issues here. We got like 12 copies of you sort of on a loop. But I think I did decipher your question. Maybe you can give me a thumbs up. That you were asking 1 meter per second is all well and good, but why stop there? Why not push even more precise than this? 0.5 meter per second
or why not 2 or 3 meters per second?
Right, okay. I think the answer is indeed on some objects will be limited by things outside of the instrument. So certainly some objects we don't hope to get any better than 3, 5, 15, maybe 50 meters per second, just by the intrinsic scatter, the noise in the source itself. But for some, we really hope to achieve, let's say, like a very quiet star that doesn't have this intrinsic noise. We do hope to achieve 1 meter per second, or indeed better. Let's say we will be happy with 1 meter per second, but we'll be even happier if we're yet to reach the limit at that point. But setting the target at 1 meter per second really comes from several of the science goals, the particular science cases that have been defined for the Marvel system.
Thank you. And in view of the audio, I think I will stop asking questions at this point. And any I have, I'll put in the chat.
Okay, thanks, David.
Thank you very much, David. So I'll give now the word to my colleague, Julia, to continue the discussion.
Thank you for the nice presentation, nice work. So quite polished piece of science. Okay, what's up? Okay, maybe first about the telescope. This may be also interesting for the public. Like, what determines the size of the 80 centimeters? Like, why smaller, why not bigger? Is it only euros or?
Let's say on one end of that scale is euros, a combination of euros and availability. So these are commercial products. 80 centimeter telescope, you can I said, if you were a very rich amateur, you could go out and buy this. In terms of setting a minimum size, it's really about collecting enough photons to do the measurement that we require to do. So going much smaller then limits you like to only the 10 brightest stars in the sky, I would say. But having 4 80-centimeter telescopes is equivalent to a 1.6 meter single telescope. So it's a little bit bigger than the existing Mercator telescope, which is 1.2 meters. So it's around this kind of size.
And does it not also determine, let's say, the angular resolution in space?
Yes, it does,
but you can see.
But we're limited there by just the seeing in the atmosphere. So the atmosphere blurs a star to a particular size. At La Palma, this size is relatively small. It's quite good seeing, I would say. But the size of the telescope is not the limiting factor here at all.
Mm-hmm. And the number of telescopes and the distance between them, does that matter?
The distance between them not, because we don't use these as a coherent imager or anything like this. The number of telescopes plays into the spectrograph. So we have our 4+1 traces in each order. If we had an extra telescope, suddenly we start running out of room, like seriously. So 4 telescopes was kind of the sweet spot in that regard.
Then the stability, or the opposite, drift, you don't want drift. I guess most of the drift can be connected with temperature, thermal expansion, and other things. Are there better choices for materials for thermal expansion, or differences between materials? Like, in buildings, people use concrete and steel because they are compatible. I don't know in optics if there's also something like that.
Yeah, so we care about the expansion of the optics themselves a little, and we care about the expansion of the mounting structure, the optical bench that is on a lot, just because it's a longer surface, and so you get a bigger fractional effect from this. We use actually not the best choice in terms of thermal expansion for this. We use aluminium for material. So this is expanding and contracting quite a lot, relatively. There are other instruments, so KPF that I mentioned at Keck in Hawaii, this entire spectrograph is built, the structure is built out of material called zero-dur, which is a glass ceramic, which is built to have zero thermal expansion at a particular temperature. And so that would be a very good choice in terms of this. There's trade-offs as well. We choose aluminium over something that expands less. Well, it's also for Euros, but we care about avoiding any thermal gradients in the thing. Aluminium is a very good conductor, and so we basically ensure that everything is at the same temperature.
In that sense, like, let's say for your successor or whatever, where would it be better to invest in, let's say, the construction of the actual inside telescope, or maybe better to invest in the nearby environmental temperature stability?
I think it's going to be in the environmental stability for sure. So this is keeping this stable. Well, I'll explain a little bit about the system that we have on the mountain there. We have a dedicated spectrograph building, inside which there is sort of 2 rooms. One is in front, one in the back is then air conditioned and temperature controlled to a certain extent. Inside this, then there is a refrigerated room, kind of insulated system. So another level of thermal stability. And then inside that, yet again, is the spectrograph vacuum vessel. And so these nested levels is the plan to then keep each of these more stable than the last. And so we hope to that nothing inside the last layer is seeing shifts more than a fraction of a degree.
Okay. Well, okay, so the technical, and you also design grating by grating, I think. I was just wondering, what makes a grating to be a good grating? So you have like a staircase profile. Should it be like a sharp staircase, a smooth one, or are there any, let's say, design rules which can help?
For this particular type of grating, the sharper the staircase, the better. Is directly related to the diffraction efficiency, how many, what fraction of light you get back. So
Sure.
the sharper the better for this particular type of grating. Yeah.
Okay, thank you. So, questions?
Hi, Jake, very nice presentation and very impressive technical work in your thesis. I was really impressed by the details of all the analysis that you have done. I will start by a question which is connected to the one of David. If you assume, let's assume Marvel is observing a quiet star, and you are limited by the instrument, what's limiting Marvel to 1 meter per second? And maybe you can go back to your slide 16 where you have the different things that you have looked at for your design. Can you comment on the instrumental limitation for this 1 meter per second?
Yeah, so I think it's a tricky one to answer before the instrument is built, because it could be a number of things that end up being the limiting factor. In fact, we play the game of hammering down the tallest nail out of many nails until everything is more or less equal here. So I think it's tricky to answer. My guess for the system as it will be built is that our illumination stability of the system is going to be the limiting factor. So the way the light comes out of the fiber into the spectrograph, let's say it shines differently on different parts of the grating and the prism, and neither of these two optics are perfect. In fact, let's say they stopped a mile short of being perfect. And so any variation in illumination there directly imprints some small shift, but certainly at the level of meter per second. That would be my guess. Time will tell, I think.
Now, in terms of science goals, if you had to choose between 4 80-centimeter telescope and one equivalent 1.6 meter RV instrument, in terms of science goal, which one do you think performed the best?
So the benefit of having 4 small telescopes is that we can, in principle, point all 4 at a different target. But this limits us to really just very bright targets. So if you're going to use Marvel in the case of 4 separate targets all at once, there's only so many cases you can do this. We point all of them at a single target, then yes, it's equivalent to 1.6 meter in collecting area, but actually we see some extra benefits here. The magnification of the star image, the seeing disk onto the fiber at each telescope for our telescopes is much less than it would be on an equivalent one. And so we would have to do some kind of slicing of fibers or something like this to get the same resolution. The spectrum would end up looking similar when you get a similar split at the end. but I think you lose in coupling into the fiber. Having small telescopes, small fibers, this may end up being a win in the end in terms of efficiency, in terms of particular science goals. Well, we measure the same spectrum with roughly the same number of photons. I think it's a wash.
Okay. For the grating, it's obviously quite big, as you have shown. Can you comment on what is constraining the size of the grating and as the instrument?
Yeah, maybe I'll find a slide. Okay. The size of the grating is really related to the size of well, it's the same size as the beam inside the spectrograph. If we want to have the resolution that we have, 90,000 in this case, with the fibers that we use, so a particular size of fibers, you need a beam that's a particular size. It's just all about magnification of the slit, the fiber itself, as a fraction of the grating's dispersion. And so for this resolution with these fibers, that size is set. The grating has to be this size.
Since we are on this design and we've done a lot of work to derive the tolerance of all these optics, can you comment on the most critical optic tolerance-wise to manufacture and on for the performance of hardware?
Yeah. I think there's two answers to this question. There's what's the most critical in terms of manufacturing the optic itself, and there's the most critical in terms of alignment within this system here. So the most critical alignment is between the fibers at the injection, between the fibers and the collimator, this guy here. So fibers to collimator. This alignment is, in fact, the one critical one in the system. The rest are significantly less sensitive to alignment errors. The other question is harder to answer. So because we got, like you said, it's you or Chris that says that the grating, we don't design the grating, we buy the grating. So in that case, we couldn't really specify that it has to be of particular quality. So it's kind of hard to answer that half of the question. In terms of manufacturing these, a lot of them are just kind of at a best effort level. It's hard to guarantee that we get them of a particular level.
Okay. Maybe two last questions. One on the EPF, you showed that the drift in the stability. What does it mean for calibration? How often do you calibrate data?
Yeah, it means that so it doesn't kill you for calibration. If this drift is happening, some small bulk drift and then maybe a chromatic effect on top, you can trace this, you can kind of follow this day by day, use it on a short time frame to track the drift of the instrument on top of this. That's no problem because the drift of the calibrator is much slower than that. But then using it on the long term, that's where it becomes a challenge. You can't then trust such a system as the sole calibrator of your instrument. You need something else to anchor this. It's tricky.
So long term is how long is weeks or months?
Would be starting at sort of the months, 1 month and longer level, you start to see
Okay, and last question. So you mentioned in the introduction the power of combining transit and radial velocity. And you mentioned also direct imaging, which is also difficult. Do you see also any advantage of combining radial velocity with direct imaging? Because we are getting there on this RV, we are getting longer and longer planets, for which we can also have direct imaging observations. So, do you have any insight on this?
Yeah, I think there's always something to be gained with combining these methods, even if it's just constraining the orbital parameters, orbital inclination, for instance, and things like this. I think the synergy between direct imaging and radial velocity is less than between transits and radial velocity. With the transit, you really get the inclination for free, more or less. You know that you see this system edge on, and so you then know that your radial velocity is the mass and not the mass modulated by this. So to me, those two together make a whole lot of sense. The others are, there's maybe less of an obvious pairing between them.
Okay, thank you very much.
Right, so now maybe the supervisors have some questions for Jake. So who would like to start?
Official supervisor. Thank you for your presentation and, of course, all the work you've done to make a marvelous success. You had to worry about many things, throughput, stability, maintenance, and so on. So, what of your design choices have been now with the thesis defense are you most particularly proud of?
That's a tricky question.
There are so many that
I think that there's not one thing that immediately stands out, but it's like, maybe not a perfect analogy, but death by 1,000 cuts. Everything kind of together. There was a lot of small incremental micro revelations that came out along the way that I think made this. I don't know. Maybe that's what I'm proud of, is looking at the thing holistically and being able to do a whole bunch of different things.
For these elegance, it's quite elegant.
Yeah, I think I pointed out that the white triple relay generally is incredibly elegant, and so it's there's a lot to admire about these kind of systems.
Okay, that's a very modest answer. The other way around, of course. Also, what would you do differently
So
if you had more time and money?
More time. How much more time? How much more?
That's up to you to decide.
Not usually the case. Okay. I think that there is a significant change that I would make to this system. So nothing about all of this that you see here, the optical design itself, would need to change. But the whole gravity vector of the whole system. At the moment, this, as you see it here, you're looking top down on this system. I would mount it side on like this. This, to me, makes much more sense in terms of keeping the stability of the system as good as possible. In terms of if anything in the structure shifts under gravity, so deforms, sags. At the moment, this sag is imprinted directly into a shift in the spectrum. Whereas if you mount it side on, this is not the case. A sag or deformation under gravity imprints nothing in principle. So that I think is it's quite a big architectural level change to this system, but it doesn't actually change the optics at all.
Okay, thank you.
I know Chris disagrees with that.
Sure. Hi. I disagree, yes. So, if you care about gravity like that here, then to me the question is, what time scale changes do you care about? I mean, for Sag under gravity, what do you like? What are you worried about? Like, how quick do you think stuff changes under gravity? And is it going one way only? Or do you worry about like dynamic changes? And how does that compare to over which timeline the instrument is to be stable and how well we can calibrate?
Yeah, I think that my worry with it is that it's the angular shift that you need to imprint something that kills you in precision is so incredibly small that you can't model this. You can't trust a simulation of the instrument at that scale.
Absolutely.
And so that's where my worry comes from. Clearly it works. Some instruments, they do it exactly like we do with Marvel, but it works. Just for the general public. But I always wanted to build one sideways instead of flat. It makes a lot of sense.
It makes
Yeah.
a lot of sense, but from this argument only,
Mhm.
right? In terms of the optics mounts and the symmetry of everything, things become harder. There's a lot that are harder. And I mean, my argument would be, okay, so maybe the aluminum or the mounts deform under gravity, but wouldn't you assume that they just slowly go one way and keep going that one way and they just keep going forever that way? But they never come back and they never like randomly move more tomorrow than today.
Yeah.
I mean, if it's SAG, if the word you use is what you assume, then I would think it's a monotonic drift. Monotonic drifts we have in other things too. Monotonic drifts is probably the easiest to calibrate.
Yeah, so that's true. I think it moves monotonically on say one direction, probably slowing down over time and then reaching a point where it stops. This is easy to calibrate, you're right.
Right. The real question is, are there thermal, if you have, is there a cross-link between thermal instability and gravity that temperature going up and down makes stuff settle in the gravity direction, in the gravity of the direction, and are there twists in the bench? We've seen stuff like this with Newell, and it's just very hard to say.
Yeah,
I think, but it's also quite a bit cheaper to do it the way we're doing it here. And so for the extra dollar spent, if you had extra dollars to spend on hardware, then I'm not asking where would you spend it, just between the detector system calibration. Would you rather spend more on calibration or more on the detector, including Google?
again, I think it depends on the exact amount. I think
$500,000.
for that you're not getting a
10%.
laser frequency curve calibration. So
It was a carefully chosen.
yeah. I think understanding the calibration system is really going to win a lot of points in terms of getting to the precision that you need. This assumes that the detector is good. Now, you know as well, better than I do, that you can't know these things until you know them. That it's hard to predict how this thing is going to behave. My feeling is calibration system on that one.
Yeah, I'm worried about that. Calibration system, I have a question on that one. You mentioned earlier that with the Holocausto lamps, you know, a few meters per second, and you said iodine, you mentioned 15 meters per second. Now, I've seen iodine results better than this. They come at a price. Iodine in itself, the absorption spectrum is stable. And there was a recent paper by Dr. Schmidt, which you may not have read. But you want to comment a bit more on the, I mean, people have found smaller planets than 15 meters per second before heterodox and laser frequency combs came about. So it's hard work, but most technologies can go down there. You want to expand on this?
Yeah, I think there's the numbers that I put up are sort of ballpark figures. I think there are outliers from this in both directions. Some people get much better than 15 meters per second with iodine. Some people never crack 30 meters per second. Comes down to instrument, the telescope, everything else as well.
But if people can do better than 15, that means the iodine by itself is stable enough. And the holopathic lamps are stable enough. It's just the people that.
Yeah, it means that particular iodine cell and those particular holocaustical lamps are better intrinsically than that level. But I think that's not true of all of these lamps and cells.
So I agree. Do you think iodine cells, that can be an instability issue on the cell itself? Between cells or aging of the cell?
I'm not sure, I'm not familiar enough to know how much these can change with aging between cells. I think there can be a small difference, but maybe not at that level.
I think between cells there can be quite a big difference, but the cell by itself should be stable to, the line should be stable to well below the settings, just no one can extract it at that level. And you need so much more signal to noise. And that's really the price to pay, in my opinion. But I mean, we have not added one to this system, and there was this recent paper by Tobias Schmidt who argues that everyone should have one as a ground truth from a different perspective, which I think is problematic in many ways. But it's interesting that they think iodines, because they're clearly fans of iodine. We're not one of them.
Thank you. Yeah, thank you, Jake, for the interesting presentation. Maybe just two very short questions. You've worked on a lot of different things. You've done a lot of things on the way to your PhD. Is there one thing that you found that really surprised you in this process that came as a major surprise into your work?
I think working on the KPF echelon and seeing the drift or the lack of drift that we seem to see on this was a big surprise to me. I was expecting this to show drifts like the other published systems that would rule this out for what we were discussing, using it as the main and only calibrator and anchoring it in one place there. But we don't see this, or we think we don't see this so far, and that's surprising in a good way.
Okay, I'm very happy with it. Was surprising. And then one other question, and with all things you've done, you've worked indeed on a lot of things. Where do you think is your a lot of people are also working on similar systems. There's a lot of activity going on. What do you think that is your major contribution to the field of proper spectral design and everything that's related?
Yeah, I think there's maybe two parts to this. So I mentioned before the sensitivity of the alignment between the fiber and the collimator here. I worked also on how do you illuminate this thing in the ideal case to get the best performance for a long input slit, several input fibers in our case. And finding that this, it's a small detail, finding that this particular, the best way to illuminate this is at an angle and not straight on, as seems like several other instruments do. That I think is very interesting just by itself as a little single piece. Aside from that, I think the design of the camera optics of the spectrograph, so that's this part here. This here is just a mirror, so just a flat mirror, you can ignore that. So these lenses here, I think the design for these is for such an instrument like this, with a large field of view, you have big detector, lots of fibers, a lot of cross dispersion. The camera here is as simple as it can possibly be, I think. And so I think that's something that maybe people can look at for future instruments as well.
Okay, thank you.
Thank you. I have also a curiosity question. So you've done marvelous work on this technology actually to measure these tiny spectral shifts. But ultimately you want to look at exoplanets. So I was wondering, these planets, I suppose they are also part of planetary systems. So are there any limitations there, or how, to which extent the presence of other planets that are surrounding the star are going to impact the accuracy and precision that you need, or I don't know, are there any implications there? How many planets can you detect actually?
Yeah, so if you have several planets in a system, then you end up with a more complex signal. So instead of a sine wave or something that's more or less has one period, you end up with the sum of many such waves, and with planets with orbits of different eccentricities, this can look very complex in the end. So it becomes an issue of modeling these. But in terms of the precision required to detect it, I think that's less of a limit there. It's the ability to model these, maybe you need more data points, you need more measurements of a complex system to fully disentangle all of these planets independently than you would for a single system.
Thank you. And this is a public defense, so now the audience has a chance to ask questions to Jake. That's all I have questions.
Jake, really excellent talk. I'll say as a non-expert, this is very clear for me. A couple of quick questions for you. So you have 4 telescopes in operation. Can you calibrate them on the same source? Can you use them all at the same source to calibrate in between them?
So we can look at, the main operation of this facility will be to look at the same star with each of the 4 telescopes. There is not much in the individual telescopes that needs to be calibrated. So the coupling into the fiber, yes, this should be aligned, it should be efficiently coupling, but there's nothing in each telescope assembly by itself that impacts the radial velocity signal. It's much more the spectrograph in here, which is just one thing. So in terms of calibrating one against the other, I think not.
And then my other question was, you had this plot that showed the improvement over time, and then you capped out at the 1 meter per second. You popped on a few times. If this cap is coming from, the bulk of stars, not any stars that have a lower noise level than this, what is the future of this high precision wavelength calibration? Is there much point to going to deeper levels? Is it thought that we can maybe model out this set of noise, or is this going to be just a baseline that we have to really get past?
People do already, like there have been some results published that show pushing past this barrier for sure. Like even on data that was previously published that noise level showed up. Now with modern modeling techniques, understanding the stellar activity better, being able to understand individual spectral lines at the level, or maybe not individual lines, but small groups of spectral lines at the level of 1 meter per second, rather than the entire spectrum. So disentangling each part and pushing down this way. There's lots of avenues for that. A lot of it comes, let's say, after the instrument in terms of understanding the data, the modeling, all of this kind of stuff.
Thank you.
Okay, more questions? No? If not, the examination committee will withdraw for a short deliberation. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy and astrophysics. Jacob Harold Pember has presented to the faculty the PhD thesis on the topic The Marvel Exoplanet Array, Technologies for High Precision Radial Velocity Exoplanet Detection, in partial fulfillment of the requirements for the PhD in Science, Astronomy and Astrophysics. And Jacob Harold Pember has defended this thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of the KU, I confer upon Jacob Harold Pember the degree of Doctor in Science, Astronomy and Astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described by the ALEA European Code of Conduct, reliability, honesty, respect, and accountability. I close the session. Your certificates, the temporary ones. You will get a pretty one by post a bit later. And I will also ask you for a signature later on this document. And so you'll have to sign it here as well, and then send it to the faculty. Yeah, so I'll leave it to you because it's your interest to get it done.
Yeah, sure.
Congratulations again. And I suppose the supervisors would like to say a few words about Jake and his work.
I will start with this. So, for those who don't know me, I'm the Australian supervisor of this map. So, me to say the first few words here, and I want to reflect on how we first met, which is so long ago that I don't know when, but it must have been about 2018. And so, young Pember here. You were an undergrad student, and I think in class, and it became reasonably, it became obvious reasonably quickly that he's a clever fool. And so, I think I offered you some vacation scholarship project, I mentioned it. I didn't randomly, so we did a project together, and unlike how this usually goes, we liked it. Next semester. And at that point, unfortunately, news had gotten around that he's smart, and other people were like, "Do you think if he wants to go on and wants to do with these?" And I was like, "He did the project with me, fine." And was able to carry this through to the master's thesis, where we did our first spectrometer together. So the first of some 3 to 4 by now. I hope the first of many come. But I think it was really a lot of fun to work with someone of his skills, his hands-on experience thing, who just went to lab and got stuff done. It was great. And then Gad visited and approached me about Martin, and you were around. And that could work out very nicely. He already has bigger spectrometer. Let's make a bigger one. And so I was like, design a bigger one. And that just happened. It was great. And then against his will first, we thought about the Cotogen. And he didn't want to go first, and now I think he doesn't want to come back. I really think it's a great loss to us in Australia. It's awesome to see how things worked out for you here, though. I hope that, you know, not only scientifically, it made you grow personally, and it was a great experience as a whole to do a PhD. It's not obvious to me that everyone wants to do a PhD. I remember distinctly when he mentioned that he had a degree before. He's a very broad personality. He did music before. It's like, if he thinks that music is not a career and he thinks he should go to astronomy, maybe he's not that clever. Okay, questionable. But I think it worked out right. And during the course of the PhD, about halfway through, it really changed from a supervisor to student relationship to a peer-to-peer thing. And that I enjoyed greatly, that I think Dad enjoyed greatly, the other people worked with him. Really seeing how this all worked out and how independent and just an expert in the field Jake became one of the best things of my work, to see how people really get into it and become awesome. And I remember the first time that he told me something I simply did not know about spectrometers, which doesn't happen a lot. Because the thing about telesensor is you have to photoplane. It wasn't the first year I thought, oh, fun, so now it gets a but it's also something that like having this realization of, okay, he knows now more than me about my field of expertise. That's that was good. And I really enjoyed working with you professionally. I really enjoyed getting to know you as a person. We worked together for some 7-8 years now. It was a lot of fun being at various telescopes. I hope it was really fun for you too. And yeah, I hope there's more to come. And thank you very much for my
I think there's really not much to add of all these words on this, which is very short from my side as well. I appreciate your work a lot. I was extremely happy when you decided to come over to Belgium. I know it was not obvious, and I also have to maybe also in apology. I know it was not simple to come over to Belgium. You even did not feel very welcome by Belgium in general because of all the administrative hurdles. Well, I hope you got over that. Also, sorry to Sarah, because there's even suffered more from this, I think, than you did some aspects. So I hope it goes better next time when you move to Belgium. As anyway, always, even if I would have. No. Okay, even if I'm sorry to see you go, well, I hope it goes very smoothly and that you will enjoy your time over there. So I also have that I really enjoyed working with you. It's really fun to have you around, to learn from you actually, just like Chris mentioned. This was really a nice thing of having you to do, but also to see, to learn new things myself from what you've been doing. So I liked it a lot, and I really appreciate your work. It's enormous. I don't think it's, actually in the beginning of the project, at one point Chris said, I have a student from Marvel, now we finally can go ahead. And because he came up with you as a master student, and in hindsight, I have to admit that I don't know how we would have gotten where we are now without you. It's very clear that this project would not have, I don't think it would have survived without you, so thanks a lot for this. We still have a few hurdles to cross. I hope you still will give us a little bit of help with this. There will also be a lot of other people trying to make it to the end, but I think we will do this in the coming years. So thanks a lot and good luck with the rest.
Is it my turn? My turn now. I didn't prepare anything for this. So it's a bit freewheeling, try and cobble something together on the fly. Yes, when I first met Chris, I was in, I forget what class it was, astronomy 2 something, one of these number codes. And I was sitting in the class, and this dude walks in, maybe struts in is more his style. And I think it was one of the first things you said. This was, I think, the first class of the semester. He's like, all right, how many of you have ever thought about doing astronomy instrumentation? 0 hands. And then he goes on this sales pitch of like, you'll never guess how much time I get to spend traveling around the world, going to cool places.
I recommend it to anyone.
And I mean, at the time, it sounded like a cool thing to follow up on. I already knew at that time that I was keen on lab stuff, lab work, doing a bit more hands-on than pen on paper kind of stuff. And so, yeah, everything I think flowed from that. I took a summer vacation scholarship with Chris, and then I think another one, and then a master's thesis, and then started the PhD, and then he was the one that convinced me that moving to Belgium might be a good idea.
It was really David. You didn't believe me. I had to track you to David. Actually.
Yeah, that's true.
Yeah, I remember standing with David. I was like, you tell me.
But I was keen on the idea of the project and spending a bit of time in Belgium, but maybe not fully relocating, because to me that sounded insane. In the middle of a PhD to move to the other side of the world. But very glad I did. I think Sarah and I both very glad we did. It certainly has changed our lives big time. So yeah, I think from the minute I arrived in Belgium as well, well, he had picked us up from the airport. How good is that? How many supervisors would go out of their way to drive all the way to Zaventem Airport? But yes, from the first minute of being here, I felt very welcome, if not by the government, by the staff, by the staff and the other PhD students in the institute. So it's been a really great experience for me. Yeah, that's all I've got. Thanks. I do have some gifts for you guys as well. And also the rest of you. For you, not Australian one. Yes,
yes. That sounds. That looks very nice.
You have to sign that. Yeah. This one. And then maybe I take it back.
Yeah, okay.
And you can enjoy your. It's okay. I'll take it back and send it to them.
Just that one. These are mine. Huh?
These are yours. So these are your temporary certificates. One in English, one in Dutch. On a nicer paper.
You got something little for you. God's
Sinds je voor een kamer nog even kan je gewoon met het it's all good.
It's something to enjoy your remaining time and something silly but longer lasting. Okay. It's from those plus. That's fine. We hope that you're kind of good.
All right, we can go out. Have a drink.